delta t, which is going to be 8,600 over 4. So I'll take this and divide it by 4. And so my slope is 2150. Then I can also tell that when time is 0, I'm starting at 28,200. All right? And so here's my B, here's my M. And so my population, P of T, will be equal to 2,150 T plus 28,200. All right? And that would be the formula for my population. Now, in 2014, they want to know what, if it continued with this trend, what the population was in 2014. So again, I'm going to go 2014 minus 2008 is equal to 6. So my time here is not 2014, my time here is 6. So if I find P of 6, that's going to be 2,150 times 6 plus 28,200. So I'll get 2150 times 6 plus 28,200 is equal to 41,100. So in this year, it would be 41,100. Okay, so in the year 2014, it was 41,100 if the model continued. And then it says, identify the year in which the population reaches 54,000. So here, I want my population to be 54,000. So you try that one on your own and then come back to the video. So we want this to be 54,000, and I want to know what year it is. So again, 54,000. So the population is 54,000 is equal to 2150 T plus 28,200. So I'm going to subtract the 28,200 from both sides. So that would be 54,000 minus 28,200 is equal to 2150 T. And then divide both sides by 2150. And that gives you 12. So again, the time here would be 12, but remember, I have to add that to 208, so it's going to take 12 years for it to reach that population. So 2008 plus 12 is equal to 2020. So this would be the year that the population would grow to 54,000. All right? Now, the next type of problem that we're going to use is going to be one where it makes it easier if I draw a diagram. It says Emma and Emmanuel start at the same intersection. Anna walks east at 4 miles per hour. Okay, so she's going 4 miles per hour east. All right. While Emmanuel walks south at 3 miles per hour. So he's going 3 miles per hour and he's going south. they are communicating by a two-way radio that has a range of 2 miles. How long after they start walking will they fall out of radio contact? All right. So now we need to find how far they're going. Now, remember, distance is equal to your speed. This is miles per hour, right? Miles per hour. So my distance is going to be my speed, or my rate of speed is what they usually call it, R, times the number of hours that I go. So her distance is going to be 4 times t. His distance is going to be 3 times t. And then they want the how long will it be before they are 2 miles apart. All right. So since this is given as a speed, to make the distance, I have to multiply it by the number of hours that they're walking. This also given as a speed, so I have to multiply by the number of hours that they're walking. And then they're going to be 2 miles apart. Now, notice that this is a right triangle. So I can use the Pythagorean theorem. So a squared plus b squared equals c squared. So this would be 4t quantity squared plus 3t quantity squared is equal to 2 squared. So that's 16t squared plus 9t squared is equal to 4. All right? So if I add these together, these are like terms, so this would be 25t squared is equal to 4. Divide both sides by 25. And I get t squared is equal to 4 over 25. Now, we're going to take the square root of both sides. And normally I would have to do plus or minus, but in this case I'm not going to, because this is a time, and you can't go backwards in time. So t here would be 2/5 of an hour. Now, 2/5 of an hour is your answer. If you want to kind of get how many minutes that is, we can use unit conversion. And I know that 1 hour is the same as 60 minutes. And so you put hours in the bottom to cancel with hours. And then that would be 120 divided by 5 minutes. So, using my calculator, I have 120 divided by 5 equals 24 minutes. So it would take them 24 minutes before they would be walking for 24 minutes before they would be out of range. Okay? And then the last thing in this section is talking about modeling sets of linear functions. And they don't go into an exactly how to solve this, but they just give you an idea of what you're doing. So let's say that we were trying to figure out two values that were equal to each other. So this is sets of linear data. And so if I had one set of linear data that looked like this, and another set that was started up higher but went down, then I'm looking for the point that they intersect. And so when you have two lines that are going together, they intersect at one point. So this one has one solution. Now, you also have the possibility that you have two lines that are parallel. And notice if you said, I'm looking for where they come together, where do they intersect? Well, they never do because they're parallel lines. So this one would have no solution. And then the last one would be where one line is right on top of another. And so that would have all of these points would be solutions if the equations were exactly the same. And so this one would have an infinite number of solutions. Right? And so this is when, let's say for example that you wanted to rent a moving truck, and on one of them the original cost, if I extend these lines to the y-axis, the original cost, and it would be like this more than what I had drawn first. So the original cost of the first truck would be higher, but it costs less per mile. And then this one would be a lower original cost, but it costs more per mile. And you wanted to figure out, well, which truck do you want to use for moving? And so you could figure out the number of miles. If you go, notice if you go M number of miles here, this truck would be less because it's here below the other one. But once you get past that M number of miles, notice that this first truck is now going to be more expensive than the other one. And so it's problems like that, and we'll talk more about those later on in the year.